We're live.
We are
All
live.
right. All right. Well, hey, this is the first Wolfram Institute live stream. So welcome to all of our live viewers. Today we're going to be discussing a particular project within our overall metamathematics project. And so I can provide, allow me to provide some brief background about this project just so that viewers who are new or people who are learning about the Institute or our research for the first time have some understanding of what we're doing so that they can better follow us as we begin to discuss this. So okay, so I'm by the way, I'm joined by two of our fellows at the Institute, Nick Merzin and Carlos Zapata. Nick and I both previously worked at Wolfram Research with Stephen Wolfram on metamathematics, and the metamathematics project was really our first multi-computational meta modeling project that extends the paradigm of multi-computation beyond the physics project. So for those of you familiar with the physics project, you have the application of these rewriting rules to some particular candidate spatial structure, and you can apply those rules to different parts of your spatial structure. And so you can actually take this kind of generation of space that you're modeling and you can disaggregate it into many distinct computational evaluation paths. And this is used to model relativity and quantum mechanics in the physics project. Um, we then began to think about whether or not this could be generalized to the study of other areas of science, technology, et cetera. And so we began with metamathematics, and here one gains a multi-computational model when one has, say, axioms or theorems, and one can entail not only different theorems, but there are actually many different paths often that one can take when one does such entailments. This is kind of a basic understanding of the kind of multi-computational impulse or instinct that led us to consider modeling metamathematics in that way. Now, one thing that we began to think about as we were modeling metamathematics is that one can begin with some set of axioms, and one can entail the theorems that can be proven from those axioms and intermediate lemmas, et cetera. So you're kind of growing this entailment structure, this mathematical structure, from these kind of seeds, from these rules that you're given and these initial conditions that you're given. But then, this is really not dissimilar to other forms of meta modeling that we do. That's either just computational or multi-computational, where you're beginning with simple computational rules and you're examining either the behavior that's consequential from those rules or the kind of structures that you can build up from those rules. And so then the question is, we know that axioms in mathematics are imposed arbitrarily to some extent. Even etymologically, if you look at the kind of the etymological roots of the term axiom, it's basically something that is just given. It's a kind of a supposition. It's just kind of presented, and you see what the consequences of that initial choice are. And of course, mathematics has been unreasonably effective, and humans do seem to be good at picking axioms that are high performing. But nonetheless, the performance of the mathematical systems that one gets from axioms does not, in of itself, necessarily guarantee that axioms are themselves foundational. And in fact, we began to accumulate some small pieces of evidence that that axioms are not themselves foundational. So just to give a kind of example of this, Stephen did write a book on these these things called combinators. He wrote this book actually, I think, uh, 2 years ago. Combinators are very, very simple formal systems. They predate Turing machines. They're very simple computations. They involve just these S's and these K's. The choice of S and K is arbitrary. If I was a better historian, I would know why S's and K's were picked. I actually don't know why they were picked, but it could be an up
Bird
triangle or a down
names.
triangle.
Bird names.
Really?
Yes.
Okay. Okay. Well, but it could be, I mean, it could be any symbol. It could be, it could be the Coke logo and the Pepsi logo. It could be anything, right? The point is that, it's a very highly simple form of computation. And what was found is that one can emulate uh, these two input Boolean functions. So, true or implies equal and NAND XOR not, et cetera, et cetera. And so this was something that was found um, during the research process that ultimately culminated in this book. Now, um, because we can we can emulate this much of Boolean algebra, the next question is, if that's the case, it should follow that one should be able to emulate Boolean expressions themselves. With combinators, one should be able to emulate the axioms of Boolean algebra using combinators. And then the question is, as soon as one is able to encode to the axioms of Boolean algebra, where you're not using wedge and v and negate and equal symbols, if you compare combinators to the kind of the I would say the kind of all the equipment that you need symbolically to to actually formalize Boolean algebra. Combinators are much more parsimonious. They're much more minimal, and so in some sense they're more foundational. And so I mean, one of the first goals that we have in sub-axiomatic foundations is just to do that. We actually did have a rather precocious student at the Wolfram summer camp who began um, uh, because I suggested that he do this. He began to do research on emulating these expressions of Boolean algebra and the axioms of Boolean algebra. Kind of, generally, it would be good to just have a function where you could give the expression and you get the combinator version. So that's something that we're going to begin to discuss today. And I will just say a few things, I guess, about the kind of intrigue of sub-axiomatic foundations. I mean, maybe we can even show some examples of this, but combinator behavior is quite funky. We also have multi-computational or multi-way models of combinators as well, where you can consider multiple paths. But you can give a certain combinator that doesn't even have arguments, and it can reduce to some simpler combinator. And so combinators have some way of kind of going down to simpler and simpler ground states. The question is, as soon as we begin to try and do Boolean algebra, say with combinators, if you're trying to prove one statement from another, or if you just take a particular statement and then you allow it to be kind of reduced down to some sort of normal form, some sort of fixed point, the question is, to what extent, given what we know about the operators as they're emulated by these particular combinators, to what extent is the kind of residue of Boolean algebra kept in the intermediate steps, or if any of these combinators reduce down to something more simple in those combinator fixed points, do they actually still retain this residue of Boolean algebra, or at some point do we hit this kind of emulation threshold where the combinators are really no longer displaying any extractable, intelligible kind of resemblance of Boolean algebra, and we've kind of found this kind of demarcation line between mathematics and even mathematics as it can be encoded in simpler computations, and then this kind of more foundational layer where you basically just have the often irreducible or somewhat inhuman kind of subterranean of computation that does have the ability to emulate mathematics, but in some sense has behavior that no longer really seems mathematical. And so, actually, I was speaking with another high school student who's also quite precocious, named Joseph Stock, who's interested in this, and he did, bring up the questions of reductionism, constructivism, and symmetry breaking. And this was a very good insight that he had, which is, to some extent, you want to be able to reduce something down to axioms. Maybe you can even reduce axioms down to some other formal kind of a description of them in combinators, and then you can try and construct mathematics from axioms, and you want to see if you can construct, um, theorems in Boolean algebra and their proofs, construct their proofs from combinators. But the question is, at some point, as you're considering the relationship between reducing things down and computing things up, do you end up finding some sort of metamathematical sub-axiomatic symmetry breaking where it really no longer seems as though you're in the realm of mathematics and you have basically some different regime of computation that is guiding it. So this is, I mean, I think for me this is kind of an interesting question. One, because I don't like suppositions or things that are kind of just imposed arbitrarily, and I think that the study of mathematics as the kind of study of the consequences from axioms is interesting, but I do want to kind of probe what goes below it. But the other question is, we're interested in the Institute at modeling things from computational foundations, physics, economics, molecular biology. We're really interested in understanding what exactly happens when you go from kind of what we call ruleyology, the study of simple programs. This is what was in NKS. I like to refer to this as empirical ruleyology. And now the study of the ruleyad, which is this synthetic space composed from the different computations. I like to think of this as being structural ruleyology. We really want to understand what happens when you go from just pure computation to the kind of behavior that we either happen to see in our world or that humans happen to invent technologically. And I do like to think of mathematics as being this kind of abstract technology. So we're really interested in, when we study computational foundations, understanding what exactly that divide is from basically completely irreducible, borderline inhuman, just machine behavior and the world that we see. And I think sub-axiomatic foundations provides a good example for doing that. Okay, so that's the kind of grand scale philosophical interest.
Yep.
We do like to do projects that we think are interesting and carry some real gravity to them. But of course, this is not a kind of a beard scratching armchair, armchair filled salon. We want to do this in a kind of a concrete way. So the first thing to do is to go back to.
Okay, James, can I comment on some of the things that you've mentioned? Just to join in the excitement, I mean, I guess should introduce very briefly who I am. I mean, my name is Carlos.
Go ahead. Of course.
I'm gonna be joining this particular stream of research on sub-axiomatic foundations. I think it's absolutely fascinating that we now have the tools to actually go to this below deck sort of mathematics, or behind the scenes of mathematics. I think it's beautiful. I think it's really fascinating that we have this opportunity, and obviously Stephen Wolfram pioneered many of the techniques that we're going to be using, and we have a lot of his technology and all the technology his company has developed. And I think it's a great opportunity. I just wanted to add a couple of comments of what you said, because I think it was a very nice overview. One is, I think that mathematicians, working mathematicians, have actually had access to this computational level in a practical sense since notations were beginning. And the moment that you had some syntax and some grammatical rules, mathematicians were actually operating in a ruleyological sense, I would say. It's just that it was not computationally efficient, it was not computationally complete in some sense when the rules were given, and it was all intuition-based and sort of very human-centric and whatnot. But I do think that they had access to this, and the reason why I mentioned this is not just to give a historical point or to make a sort of a broader philosophical point, is that actually combinators in particular were a particular case of term rewriting systems, right? So they were built to do this term rewriting, and so they were actually combining terms which were characters, right? So that was the whole point of combinators, right? So in a sense, they were sort of important, and I think it's a good system to start investigating in the sense, because they somehow do the minimalistic operations on characters. And mathematicians realized, and computer scientists realized, this is basically what we do. We take some expressions, we manipulate them, and by the end of the 19th century, early 20th century, people realized, this is what we're basically doing, right? And we have all this beautiful early 20th century mathematics of Gödel and many other logicians. But I think it's down to the realization that, okay, we are just manipulating symbols, right? And at some level, this is what we're doing. And I think that is really the beginning of this sort of ruleyological mindset. Now the difference that we have this computational tool, literal machines that can do it now, and much more efficiently, much more broader. So that's one comment. The other comment is that I think of higher level mathematics, axiomatic mathematics. I don't know which name we should coin for this. I mean, it's the sub-axiomatic that we're trying to go after. So the typical, more axiomatic level. I think of it as the sort of user interface, right? It's you have the machine and machine code running in the background, and you have the user interface. So what I find fascinating about the opportunity to do sub-axiomatic research is that, until now, it's almost like we didn't have access to the architecture of what's inside the computer. It's like you couldn't really access, you only had access to what the programs were doing, and you said, oh, I would like this interface to be this, I would like this to do that, but you didn't have access to the, to the machinery inside the computer. And now I feel like we have the opportunity to really go into this level of, okay, let's rewire the machine, and let's see what kind of axioms make sense in this setting, and maybe we can get it to do the stuff that we like to do. And so this is what I find super fascinating about this project broadly, right? Like just thinking, oh wow, now we get access to this machine level of mathematics. That's amazing. That's a first, I think, in the history of mathematics, and it's super exciting. So anyway, just wanted to add that.
Yeah, well, those are great points. I think I've used this analogy of kind of UX, user interface versus machine code analogy. I mean, I think Stephen also uses this machine code analogy quite extensively too. I think it is a good way of looking at it.
Yeah.
It also it becomes somewhat less of an analogy actually, and more of a kind of useful, more of a useful concept, especially when we start to think about things like observer theory and bounded agents being able to actually be able to kind of extract somewhat, tractable, tangible kind of, ontological objects from this kind of underlying irreducible computation. So it actually that line of thinking is, I think it's more than just a kind of let's think about how this relates to technology. I think that it really is there is a real kind of dualism between how technologies are created and even how areas of science are built up, that I think studying things from computational foundations will help to show that. Now, Nick, I mean, if there's an intro you want to give, go ahead. But I also know your disposition, so if you want to,
I'm not a
jump
master of monologues like you guys. It's like you were speaking for 20 minutes. Do you even realize that most of the people don't even know what combinators are? So we probably have to start with some introduction to actually what we're talking about.
That'd be very useful actually.
Go right
go
ahead.
for it.
Yes, go right ahead. Why don't we do some screen sharing and
I'm not an expert in combinators too, but I guess I'm just gonna do what I usually do in this sense. In this case, when I have no idea what I'm doing.
Well, okay, but actually, I mean, we should. This meeting does have. Hold on, I'm trying to. Sorry, this meeting does have two purposes. One is just to introduce this project, but also to make some advances on the research front as well. So I think kind of introducing combinators, and then maybe taking a look at Gleb's code and we're starting to work through our assessment of emulation of Boolean expressions and axioms of Boolean algebra would be a good direction to take this as well.
No, I'm not sure where we should even start. Maybe we should just start with what actually already available. If you actually want to learn about combinations, the best way to learn is just look at what's actually there.
Well, I think
instead of
the WFR functions, I think, are a perfectly good place to start.
Yeah, that's what I.
Yes. Okay. Right.
So maybe that's like a little bit more expositional of what combinators are, and I guess what would be the best function to start from?
Combinator fixed point or combinator plot. Combinator evolve.
Maybe like a picture. It's better than 1,000 words. Let's see. Well, this kind of explains how is it. I just realized I have S. Let's just start my session from scratch. So what else do we have here?
I'm not sure that that's really the best, function to start with, though.
Maybe a brief explanation of what a combinator is and what a combinator is doing is definitely useful here. Like 2 minutes.
Oh yes, but I think
Well, I can explain this much.
Yeah.
Like I guess you can see it from here already.
Yeah, but
right?
let's
Because
start
what combinators are, especially S and K combinators are quintessential ones, right? Well, I guess an intro to S and K. And usually they describe just by a couple of simple rules like that. And it's a replacement rule, it's an expression rule, so you just try instead of using some higher level functions, you just gonna try already built-in ones. So we have a combinator like S. This is our patterns. They can stand for anything we want. Maybe it's 1, 2, and 3, right? If you're actually applying this combinator rule to expression like that, it's gonna rewrite it, right?
Yeah.
So it's gonna put X, basically copies its third argument. So that's the nature of the S combinator, some kind of copying. Okay, what is the K combinator? It's kind of also a similar thing, but instead of applying it to this expression, we apply it to this expression. This is just dropped the second argument of it. Its second argument, Y in this case. Mm-hmm. So one is copying, one is discarding.
Yes.
And well, combinator theory, I guess, tells you that those two are enough to be universally computational, right? So you can construct any program from those two simple rules.
And just to clarify, the data is string, right?
Well, it's not a string; it's a tree, right?
Sure. Eventually, yes.
Every expression. Yeah.
Yes. Yes, but the basic input of S and the basic input of K is a string, right?
No, it's not a combinator in general.
No, right? What I mean is S is past the 1, 2, 3, or the X, Y, Z. Right?
It's
as a
tuple. If you're talking about the leaves of this tree.
Yeah.
Well,
it's a tuple, right?
Even S's themselves. You can even have expressions that.
I understand. I'm not making myself clear. I'm just saying a very basic point. I'm saying that the argument that you pass S is a tuple, right? It's a 3 tuple.
It's kind of this kind of input as a whole. When I like.
Yes, I mean, what I'm trying to say is super simple. I mean, I think I'm getting lost in words. S has by argument a 3 tuple, right? A 3 string, 3 elements.
Yeah, that's when the rule cannot be applied. But
yes.
in principle, you can have this thing. It's going to be this passive thing that's nothing. There's no rule that applies to it and rewrites it.
Understand, but that's with the perspective of rewrite. Yeah.
Yeah.
Yeah. I was not trying to bring in the rewrite perspective. I was just saying that if you look at S as an operation on terms, then it's acting on a 3 tuple, right?
Right. Yeah. Okay. Another way of looking at those kind of things, instead of this notation with square brackets, usually the combinators are written like this.
Yeah. Because to say just to emphasize, because to say that it's a tree, it's actually not enough, because trees are not necessarily ordered sequentially. The leaves, right? And these are. That was my point.
Actually not. Trees are by definition have ordered children. It's the graph that have.
Okay, depends on the definition of tree. Yeah. I mean, normally in graph theory, trees are not ordered. But yes.
Talk about tree. I mean the actual tree that we have in the language, so we don't have to even argue about it.
No, right? Sure. I mean, okay, I didn't know what the tree was implemented in this language. Yeah.
Okay, let's keep going, guys. Let's keep going. Okay, so we have. Okay, yeah. We've shown the rules for S and K. So you have these rules, and then you can give. I mean, you can just as Nick is mentioning, you can feed an SK combinator. It can just be a combination of S's and K's. You can include arguments such as X, Y, Z, or Z, depending on who's listening. Yeah. Right.
Yeah.
But you can even give. You probably have some example of this. Actually, this is an example. It's not. what I put in the chat. I mean, you can even give examples where it's just S's and K's, but it happens to evaluate down to some sort of fixed point.
We just don't jump ahead. Okay, it's like we just go step by step, a little bit more elementary. It's like, yeah, there is some ways you can copy it. Okay, it's like let's see. So it's clear that we can apply our rewriting rule. Yeah, we'll get to that. Let's go a little bit slow, for the sake of the viewers or something. Or
yeah, for our own sake, just to ensure that we all understand what's happening. Fair enough.
It's beneficial to just review how we're talking about in general.
Fair enough.
So we have like a place rule that can act. Well, if you have a more complicated combinator, I think we established that we can have like expressions like this. Let me just hide it, everything junk. Completely. Okay. We established that we can have expressions like that. We still can apply it like only a single. We just call it S rule, K rule.
Yeah.
Why not?
And
right.
And to especially to guide ourselves and people who are unfamiliar with this, that would eventually evaluate to a tree of X, Y, and Z, right?
What do you mean evaluate?
Like
you have to.
So after doing the rewrites with S and Ks, right?
Continuously write. Repeat it enough.
Yeah.
Repeat it right. Yeah.
Yes.
Yeah, sure. I'm trying to get to it. It's just
okay. Yeah. But
a single
actually, but wait, I didn't know. But it might be the case that I'm not sure about the K case. I mean, couldn't it be the case that you evaluate this down to a fixed point, and there are still some S's and K's there, but they just can't. They can't do anything. So it's not. I don't think it's guaranteed that you're going to remove all the S's.
Yeah. If you write an arbitrary expression with S's and K's, for sure, you might not get rid of all the S's and K's. Yes. But if it's posed, then
That's why you even have examples where it's just in terms of S's and K's, right? It doesn't have any arguments. And then if you apply combinator fixed point or something to it, you're going to get some other shorter combinator. But it's still a combinator nonetheless. Right. So it's not as though it's not guaranteed that you can actually apply the rule. And when you can't apply the rule, you get this rule-logical plaque that just builds up and doesn't get computed away. By the way, that's part of why this is interesting from a sub-axiomatic point of view. Because as soon as we begin to actually encode Boolean algebra in terms of combinators, these things might be able to reduce, but it's not as though like you're going to reduce just down to the arguments. You might still have these S's and K's there, but again, if it's just this kind of rule-logical plaque, like, right, where you're able to, and I'm saying this like kind of arterial plaque, like in your body. It's like you've been able to kind of somewhat reduce it down, but there are all these S's and K's that don't evaluate. And if at that point that thing's not really easily recognizable mathematically, then you've probably crossed over into just kind of pure computational territory. But we'll get there. Okay, Nick.
It's like you like to like mention all these foundational things, but yeah, we're hard to understand.
We're playing off each other, right? I'm trying to set this stage where all this is going to happen and speak to some of the details. And you're kind of introducing the characters and the people who are.
So, how to merge.
Nick, one question, Nick. So in that particular expression, just to push forward, maybe finish your exposition, because I was going to ask how you write that without X's, Y's, and Z's. But maybe finish what we were saying, and then we can look into that.
Well, what do you mean? How do you write it? No, let's figure.
Exactly what James just said, that you often just work with a rewrite of the S's and K's themselves as a computational sort of procedure, right? So, I mean, maybe finish what you were going to say, and then we can. I mean, I'll ask the question in 3 minutes when you're done.
Oh, I'm not sure. I was just going to go very slowly.
I think that's useful. I'm saying do that. I mean, I think it's very useful to see it step by step. I think that's good.
I just want to remember some of the combinator visualization tools that we have.
Yeah.
So besides this kind of bracket plot, do you have something more fancy?
What do you need?
I
What are you
know
looking for?
that actually shows the matching, like combinator.
Like the colored ones
Yeah, like this thing we tried
at the beginning.
at the beginning, right?
Yes.
Yeah, maybe that's what we want to use here. So if you have an expression, it already matches the appropriate rule, right? We can specify. And what are the kind of? I think there are multiple ways to do it. Frame matches. Is there anything else? I guess that's the only frame position. Anyway, okay. So this is kind of shows you where the rule can apply, right? So where this left-hand side, which is this pattern, specific pattern for S combinator, which is on the left-hand side of it. This function can highlight it conveniently for you. What is where this kind of rule can apply? And I guess it can even extract the position. Maybe it's kind of cool, or this one. This is also nice. Let's use this. Right, so that it also shows multiple ways you can match. So there is the point of the major point of this kind of combinator that there almost always in a big expression like this, there are many ways that this simple patterns can apply, right? And there is a certain order you can rewrite them. So you have to pick one first, right? So there's one position there. Okay, let's just, okay, I'm gonna just write the actual implementation of such things. I just call this thing expression. And if you have this expression, combinator expression like this, if you're gonna try to find all the positions inside of this expression where this particular pattern matches, it can list this position, right? What it says is that now we have 3 positions that this particular rule matches. Okay, we can even map something like frame around it at all these positions, and so we don't have to use these functions that who knows how they work. Because they're pretty much, some of the behavior is pretty easy to reproduce with just the Wolfram language itself anyway, and much more explanatory, I think. So now we can see that we have 3 positions that we can apply a rule. So okay, then we can use the same exact code that actually apply the replacement, maybe just at the first position. Why not? And we use the S rule, map a replacement at the first position where it matches. And you can. It's hard to tell that it's changed, but it actually changed, because this one changed from here. Okay, and you can instead of first position, you can pick any out of those 3 positions there. Yes, I have to show it here. The 3 positions that rule matches. So there is an order to that, or you can apply everywhere at once.
Or you can apply it multi-computationally, but we'll get to that.
Yeah, well, though it's not that hard to see. So you just map over this position, and you have 3. You can put a nice column around it. Now you have 3 potential outcomes depending on which position you chose to apply your S combinator rule.
So,
right?
Just a clarification term in case we have some viewers that are familiar with terminology from graph theory and things like that, and rewrite systems and so on. So when we say multi-computational in this context, what we really mean is that there's basically a graph that is branching out of the possibilities given by the rewrites, right?
Yes.
Yeah.
We have a function. We have a function for it. Multi-way combinator. Nick, you can show that example using multi-way combinator just to visualize it.
Oh, that would be beautiful. Yeah, I'd love to see that. Yeah.
That's right. Is it the actual combinator? Do you have to specify the rules?
Let me check.
Let's see.
I think you do have to specify the.
Also, there's also
The
more
rules.
general.
I mean, just to give you an
Sure.
example.
I'll
Here's,
like this
okay,
one.
no,
Here it
you
is.
found it. Yeah, exactly.
Yeah.
Yeah, there you go. So that stays single way in the beginning, so until all of a sudden you find rule application alternatives, and then all of a sudden it goes
that's
multi-way.
wait. So, but I'm confused. So the initial state is different because we had three options in the previous one.
This is the initial state.
Ah, okay. Sorry. I
Well,
was.
This is a different expression. Let's try it.
Yeah, let's do.
Maybe
let's
like
do
just make one step.
There you go.
Oh, okay, hold on. Why it's because it's and only consider the S combinator.
Ah, right.
Now
Yes. Okay. That makes sense. Okay.
just for the
No, that's
Does that
that's a great function.
Does that go? How many steps does it go for this particular expression? What happens? Yeah. Okay. There you go.
Yeah.
Nice.
Like four is it's a fixed point.
Nice.
Just
what
for
is
the
that?
So that
let's just-
does it mean that the system was I mean the initial state was kind of well posed, that everything could be evaluated validly, or
Oh, that's the feature of the combinator. They always converge into a single vertex like that, into a single expression. They have a normal form, independent of which order you choose.
Ah.
They're confluent.
but the problem the
Confluent,
previous graph was in confluent, right?
Well, it should be
Because
confluent. You have to
because-
wait
yeah.
long.
Ah.
Potentially, you should wait long enough.
I see.
Depends-
Right. Interesting.
That's it's kind of, I guess it's like kind of short-term future multi-computational irreducibility for multi-way combinators. You know ultimately that you're going to that the different evaluation paths will converge confluently upon a fixed point, but you actually don't know necessarily when, and you don't know what's going to happen
Right.
in the meantime.
Right. And the final
Yeah.
expression, as you said earlier, will be a combination of S and K's, tree-like, and X, Y, Z's, tree-like, right? The single
We can
one.
take I mean,
the confluent
we have combinator fixed point as another function. We actually have a lot of combinator functions, which is part of why it's so good to start sub-axiomatic foundations with combinators. But there's just a function where, so we have like evolution list functions where, it might be the case that the combinator has some lengthy evaluation, but you can always just get that fixed point if you want. You can see what the
Yeah. I know, but my question is the form of the fixed point is a combination of S and K's in tree-like, and then X, Y, Z tree-like, right? Combined.
Well, but that's why I wanted to actually see what it was in this particular case.
Ah, right. Okay. Yeah. Let's see it. Yeah.
Like,
Sure.
have the K's all been computed away? What does the end result look like? We don't know.
Oh,
But in general, right? That's possible in general, right? Like it's a combination of SKs and terms.
Well, we're not going to nothing new is getting introduced. There's no W's or anything. So it'll just be terms of S's and. Okay, there you go. Now, are there many options for that?
maybe you have to specify which. Oh, this is kind of boring, but yeah, I guess.
Right. So in that case, it does evaluate to all the.
But here you don't have
It
S and K.
evaluates. Oh yeah, that's interesting.
If you run, like in that example from the multi-way combinator one, which has very slow convergence rate.
Mm-hmm.
I'm gonna try it anyway. I wonder whether it finishes in a few seconds or not. Depending on which path it chose. Maybe the particular path, it's not necessarily converge for every multi-way path, right? It's kind of ultimately what it's saying, that you can turn around at any point and still converge, but you still can choose a path that kind of continues infinitely, I think.
Oh.
Or maybe I'm mistaken. You're completely. forgotten all the combinator theory. So what are we discussing here?
Well, I mean, Nick, we're doing two things, right? One is we're familiarizing one another with combinators by us all respectively, sharing what we remember about them and what we know about them, which is good because I think each of us, I don't know, has something to say that the other person wouldn't say. So this is nice. This is fun. But I mean, I would say within the scope of this meeting, we should try and zero in on the particular case of Boolean algebra. So I mean, just to kind of maybe just to provide somewhat of an overview. Okay, so we've taken a look at some combinators. In particular, we're considering SK combinators. There's an S rule, there's a K rule. We've looked at those rules. We've looked at some evaluations. We've shown applications of the rules to particular positions. We've looked at multi-way combinators where you consider all the evaluation paths together. We've looked at fixed points. So we've discussed specific aspects of these. But maybe for someone who's watching this, who's still not quite, grasping it. I mean, Carlos made the good point that this is ultimately just term rewriting, which is we're giving some input, we're applying a rule, and we're getting some output. And the input and the output can be very complicated. And this is kind of an important trade-off in rulology, which is like the more simple, like the fewer building blocks you use, or the fewer even symbols that you use to formalize these expressions, the more complicated the structure will get, evidently. So combinators, even reading these can be complicated. The understanding the applications of the rules can be complicated, and the evaluation behavior can be very complicated. The combinators can get long, and then they can get short, and then they can get long again. So they're quite wild. That's not the end, though, right? That you can apply that further, right?
I guess so. Maybe.
Well, because you don't have K, so it's not the. Yeah. It keeps going though, right?
I don't think so. It's kind of weird feature. Maybe it's.
Well, but
Depends.
What's it look like? What does it look like when you use multi-way combinator?
Or maybe I should have done something like catenate here. That's why it's so weird. Yeah.
But why are you doing it with nest graph, by the way?
Well, just to use more elementary functions. So like I prefer elementary functions to some high order one because there's some background behind, maybe hidden from view.
I see. You like cooking your own food because when you order it from the restaurant, you don't know what they put in it. Yes.
Something like that. Yeah.
Okay. Well, Nick briefly was cooking a two-headed chicken, but it turns out he figured it out. Okay. Well, okay. Carlos and I have discussed this briefly. This is actually somewhat of a challenge that will require us developing kind of a good live stream practice over time. But there is always a trade-off between this being kind of an educational meeting for us and for the audience, and then kind of advancing towards the particular research goals that we have. I think we should turn to the Boolean.
The Boolean expression, yeah. Can you send me a link to the Gleb's post? Or just browse around?
Yeah, I have it. Okay, this is kind of I'll also, I mean, just for the sake of it, just to put it in the notebook, I will give you. Well, this is going to be quite large. What happens now? I can't even post it in the chat. I was going to share the table of Boolean functions from Stephen's post, but okay, there it is. Yeah.
Oh, no, what we actually need It's not a table, but this neat little list. Okay.
Well, but we should use the other one. Okay, so this is a little insider. How can I put this?
The more correct version.
Yes, there are two versions in the book, and I think Gleb chose the one that was in the back of the book. Did he type those out by hand? Sorry, Gleb, we're not picking on you or anything. How did he get them?
This one, maybe. I don't know. Well,
I mean,
maybe he
Nick,
extracted
I was
from-
gonna send you the. I mean, you can get it yourself. Click the copy from the actual Combinator book, but you can, of course, perfectly capable of doing that yourself.
Can I find it here?
Yeah. I mean, if you go to the post, here, Nick, here. Listen to
Oh, I have a post here, maybe. I was
Yes,
looking
yes,
for
that's
some
it.
kind of,
You were looking for something like the metamathematics book.
I don't know.
There
it's
it is.
called-
Yeah, there you go.
So this is the table. So we have a code. A complicated one that takes some time to evaluate, and it's just a
It takes time to
pre-computed
evaluate.
result.
Yeah.
And the code that actually makes this kind of neat grid. Okay. And what are those numbers? Remember? Combinated traditional form. Okay, here's the list. I just wanna actually understand how to extract the table I need. So this is the list of Boolean things,
Yes.
some unknowns. Here's the example. Let's remove the plot. Don't need the plot. Don't need the index. Anything else that's after that.
One just brief comment. I am interested in those unknowns. They're kind of like, I mean, it's funny that.
Well, it's not unknowns. They still have a name, I think, right? Like, I don't remember. Well, it's actually unknowns. It's not a Boolean.
I think
all the Boolean functions have names.
Yeah, I mean, even in NKS, I think there's the same thing in where you find these with models, and it's just interesting that there are these kind of shadow operators that don't have names that you still kind of get. Anyway, that's a good summer school or whatever project in its own, which is studying these particular. Yeah,
So
I wanted to name them.
Can we explain?
Go ahead.
Can we explain the scope of what we're trying to do here with the Boolean algebra, like in
Yes.
detail?
Well, okay. So here's the thing, right? Okay, so we have and or equal, right? Okay, but if you look at what was done in the post, they were mainly just used for truth tables. So Nick could even fish out an example from the book. It was just right above it, right? So you could do this with,
This is important comment.
This is an important comment. Yeah. Right. So
Oh yeah,
and
yeah,
this is an example.
Yeah.
So
Actually, Nick, running one of those truth tables would be helpful, even the one that's given in the book.
I
what do you
see.
mean, right?
So
Like
K is true and SK is false. I see.
Yes. And so if you take in this case, this is the operator for and so you have, true and true gives true, true and false gives false, false and true gives false, false and false gives false. So that's how they were originally used. They're originally used to construct these truth tables. But what we haven't done is anything more complicated than that. So we haven't taken these, something and not something. We have not used these to create more complicated expressions in general. And what would be really great is if instead of having to like manually, laboriously, like put them together, we just have some function where it's like I give you.
They just compose naturally, so it's,
Right. I was gonna say. I mean, they compose, right? So it's compositional.
sure.
Yeah, but we don't.
As long
But
as
we
you have
don't.
a binary Boolean expression, or at least you can very easily turn it into a binary one. You can just replace it using this table into a new combinator form, and it should evaluate no
Yeah.
matter
Yeah,
what.
I'm not saying it's hard. I'm just saying we don't. We haven't had it, and
Right.
that's the first step. Yeah.
But then what after?
Wow. Okay. So then once we have that, then we can take the first sub-axiomatic step, which is actually encode the say the axioms of Boolean algebra, and even start encoding say theorems that we know are true, or even theorems that we know are false in Boolean algebra. And I mean, there's two things. One, seeing if you can if we can do proofs with combinators, but then also starting to actually probe. If you let's say for instance you happen to take a particular axiom or a particular theorem in Boolean algebra, you express it as a combinator. We run it, we see what it evaluates to, and there's just, I mean, the next step, which does require some experiment design. So I'm not saying that the experiments
Oh,
are fully designed. We have to design the experiments, but the next step is
well,
once
let
we
me try to
have it.
explain what sub-axiomatic actually means, right? Very,
Okay.
very in simple terms, right? What we have in that Boolean table below, we're just gonna have this graph beside, so it's clear, right? What we have when we constructed this kind of a Boolean table, what we only considered is when you take like any operator like and apply it to true and false, and then run the combinator to a fixed point. So it
Yeah.
actually reduces to its normal form, whatever path you chose, maybe some
Yes.
fault order. And if it reproduces the actual Boolean table, you call it this particular Boolean function that matches it, right? That's how we found all these Boolean functions corresponding and their corresponding combinators. But
Right.
subaxiomatic means that, okay, now look, what are those intermediate steps that we produce during that reduction of a combinator, right? Do they correspond to the actual uh, Boolean expression itself,
Yes.
or it's a completely different?
Yes.
Yes, I see. I understand. Yeah. I mean, my intuition tells me that they won't correspond, right? Because in general.
Well, this is what we want to find out. This
Right.
is what we want to study.
Right.
Well, if this is so easy to just compose these, I mean, first of all, before we presume that it hasn't been done, take a look at how Gleb did it. But how long do we have? Well, this was going to be it. This was going to be an hour-long stream. Maybe we can extend this by like 15 minutes.
Yeah, 50 minutes I
Let's
think is
just
okay. Yeah.
yeah.
So what should we do?
Let's try some composition.
All right, well, it's kind of, as you said, it's already here, right? This is applying, let's review. This is applying end, this is the end thing, right? From here. So we just pick end combinator and apply it to all possible ways you can make a pairs of true and false, because K stands for true, S and K stands for false. So this is our Boolean table headers, basically, right? Enumerating all possible values and applying n to it, and then just running it to a fixed point. And that's what you get.
Yes.
Right? That reproduces the Boolean table because it's true, false, false, and false. It's only true when you apply it to double K, which stands for double true.
Mm-hmm.
So that's what running means. And I guess the intermediate expression for this particular order that like this function chose to reduce this particular expression, we can just manually see whether this thing corresponds to anything from the table. So the first thing, I guess, we have to actually extract all possible expressions, right? And just do it. Is it all the expressions? How many are we have there? No. Just gonna take this here. Without any styles, whatever. Some index, which is weird. Not gonna deal with that. I'm gonna think and remove any styling. So this is all our Boolean functions. Okay? There are 16 of them.
Yeah.
So just see this particular thing from here matches any of them, right? And the
Okay.
hold on. Oh, it's not right. There's some stupid styling inside of it. Let's just run it
Yeah.
scratch.
So a very stupid question, but just to double check, the number of Boolean functions is the number of possible truth tables, right?
The number, well, yeah, that's true.
Right.
Because you have 2 to the power of 4.
Exactly. Yeah.
Yeah. Yep.
Yep.
Yeah.
I guess I make a for convenience. Just name those so that I can now I can remove this table. So Boolean functions for and. We'll just check that. Hold on, it doesn't match this one, right? It's a different table.
Yes, that's good.
Why is it this complicated thing there here? Huh? Oh, I know, because it's unknown 1, unknown 2, unknown 3. You have to give it different names. It kind of collapses it. So now it's still
Mm-hmm.
the same thing.
What is that?
Hold on. So this is the table. I don't understand. This is the names, right?
Yeah.
Alright, I'm just gonna subtract it from this kind of list then. Now it's correct. And I give those unknown ones names. Okay, let's make this our Boolean functions. Okay.
Okay.
Okay. So now when we take Boolean functions of and, we have this expression. If we apply it to on a shorter name. Apply it to true and false. And then run to a fixed point. Yes, you always have to come down. We just make a function run. Like this. You have the whole sequence which reduces to false.
Yes.
And let's try to find something. For example, in the intermediate step. So this is our intermediate steps that you don't know. Just take it. And see whether there's anything inside of it.
I don't want to be biased, but
That matches any of those. Hold on. We have to try maybe alternatives. Okay. Or just I want to actually see. So we found, and just delete the empty ones.
Okay.
Okay. So we kind of found first there and last.
But does it count? Does that account for everything?
What do you mean?
You know, what would be nice is if we had something that could highlight these, where you highlight it with something that is still some sort of Boolean function, and then the parts that aren't highlighted, it's like doesn't correspond to anything.
Well, that's what we're kind of trying to do. See, this is kind of highlights where the last is.
Yes.
Because last and first are boring. It's basically
Just
the same.
okay. That's okay.
Right. So it's like.
Yeah. So there's somewhat of a methodological issue here, which is K. When K is first, but it's also just this elementary operation. So, okay. I mean, I guess you can make the argument that mathematical operation of taking the first thing, because it's kind of built into K, that little grain of mathematics always stays no matter what, I guess, right?
But the point here is that we haven't actually found anything that matches the whole expression. So
exactly.
So we can't actually compile it into any Boolean expression from this table. There still can't be like a parallel Boolean table.
Yes.
With similar representation or whatever. Maybe it's not
right.
because it's not unique. Even maybe for those, is it unique for the same true and false representation? Is it the unique Boolean function? I don't think so. Maybe for the same K, like we took here, K to be true and SK to be false. For this particular choice, there can be still other combinators. This is just the shortest one. In some sense.
Well, it's not going to get shorter than that, right?
Yeah, but maybe there's a longer one. Maybe that's exactly the step that we have found here. Is a longer version of AND, maybe. Right, so we have to run through all Boolean tables again and see whether it reproduces it.
Yes.
Right? So actually, we can try it. So this is our step. We generate this Boolean table like here. We just do the same thing like here. You can sell this S and K, which were AND before. It is an unknown thing. We call step. Apply this and run. Let's just run that we okay. And we let's just go to run all or run least rather. Actually I don't care. Let's just run it on a list. So I wanna take the last one. So it actually is reducing to something that was only true or false. Well, because it was a step anyway, right?
But then, I mean, one thing though is these will get more complicated when we actually. Why don't we do a truth table where we're actually composed, like it's not just true and true or true or false, but we're including like. Let's at least try something where we're using and or.
Well, I don't think it's necessary yet. So that's very interesting. Why would you go ahead without finishing this exploration?
It's because I'm impatient and I really want to. I want that general Boolean algebra capability. That's why. Just to be, if I'm fully transparent. That's why.
We're already looking at Sub-Axiomatic.
Yeah, I know.
Foundations. That's how.
Yes, I understand. But this is also interesting. It's hard. there are a few exciting things happening.
So, like, what is this Can you say what is this Boolean table to what Boolean function it corresponds to? So basically, true 1 0 1 0. Which one is it? Can't tell.
True.
It's
Is
is it
it?
checker box? Is it this one again? It's iterating.
Oh, I see.
So it's last. So it's essentially the same as last again.
What, that whole intermediate step?
Yeah. If you treat this intermediate step as a combinator itself, you just feed it the same arguments
Yes.
for every Boolean table element. It acts as last Boolean function.
Can you show that, or is that what you just did? Sorry.
Yeah, that's that's what we just did.
Okay, let's look at it one more time. Sorry, I didn't know that that's what you were doing.
Pay attention, James. Pay attention. All right. Let's review. Where the hell was I? So first what we did? We had this nicely run table just using AND here. We can actually replace here this beer and we're gonna put it above. Right? This is how we enumerate all the Boolean table elements.
Yes. I followed most of this. I just didn't know that was that particular step you were taking right at the end there.
Yeah, this is the thing that we.
I know. Yes. Yeah.
That's
Yes.
the step here.
Yes.
Right?
Yes.
We are
yes.
trying to. That's what it's called step. Then we enumerated all of the Boolean table elements and run this step for them. Right? The last one.
Yes. Right.
Whatever it reduces, and we reduce it to this
Right.
kind of thing.
No. Okay, I get that. Yeah. Okay. That's interesting.
Yeah. So I guess we can even make the similar array plot for this thing. Okay.
Okay, so I have a question that, I mean, while you're doing your code magic, I've been thinking about the experiments that we could pose. And
Yeah, there you go.
so maybe James, I don't know if you want to finish this and then I can ask, but I have a question when it comes to, so when the after step, so obviously we need to get this functionality to evaluate on expressions, but so you said that one of the motivations is that, for example, the axioms of Boolean algebra will be then, rewritten in this way, and then you can.
Yes.
Right. But I was thinking that the moment you have the truth values, in terms of, we can do them. We just did some examples, right, of truth values of these operators, just the operations, right, just the operators themselves.
Yeah.
The axioms are directly. They follow directly from the truth tables. They are not imposed in Boolean algebra. They are a consequence. They are not axioms in Boolean algebra. Actually, they are laws.
Actually, that's kind of not axiomatic.
Yeah.
That's why not really axiomatic, not the right word here.
Yeah, because they are laws. They are satisfied. They are not imposed.
No, it's satisfied because we can prove them. We just
no. They are satisfied.
Tables.
They are satisfied, but not imposed. That's what I mean. They hold. They are true. They hold. They are true. They are true expressions, but they are not imposed by axiomatically. They are a consequence of our implementation already. We will find them. We will find them. They are not axiomatically imposed. In Boolean algebra, once you define your Boolean algebra according to the truth tables, and that's why I asked, are these the 16 of all the possible truth tables?
Yeah,
because
yeah.
Once you have the truth tables, then all the laws, all the so-called axioms are consequences of the truth tables. They're not axioms in this context. That's why I mentioned the semi-group the other day, because in that case, it's more of an abstract axiom that you want to parse. In this case, it, yeah.
You can kind of also phrase it as in a model theoretic way, right? We're looking for a model that satisfies those kind of axioms.
Sure.
And we found one. You can find it by just binary numbers, right?
Yeah.
For the same, for the Boolean algebra. So this will satisfy it. But this particular model has something extra, because we can also explore those intermediate steps, even though it satisfies just on the ends of it, of this evolution step, or rewriting rules. It satisfies this particular axiom, but it also contains a bunch of stuff in between.
Yeah. I mean, absolutely. I mean, is it? Yeah. I agree. All I'm saying is that in terms of, in terms of the actual implementation of this example, we are not replacing the axiomatics. We are. I mean, it's going to illustrate the point. Absolutely. I mean, I'm not disputing that.
We go on sub-axiomatic. We fixed our axioms. Now we're gonna explore what the hell is next. So like in this case, we just the first step that we took actually showed that this reduction of while computing one particular Boolean value in the table, we went through the last Boolean function for some reason.
Right.
Just for the sake of it, find it one.
Yeah. And another question is, are we looking at the combinator expression of Boolean operators because we have two terms that are being rewritten instead of 16? Is that one of the main points of interest? Because deep down, you can have 16 element tree expressions, and then they are formally equivalent to combinators. It's just that they have 16 operators instead of 2, right? But they are formally equivalent. Maybe I'm missing something, but
okay, just let's rewind. What equivalent to what?
Yeah. So Boolean algebra just as a term rewrite system, right? You have 16 operators, some unary, some binary, right? You have these terms, right? So eventually all your...
It actually depends on what you call Boolean algebra.
No, I'm calling Boolean algebra what we are calling Boolean algebra, right? Like the 16 operators.
No, not necessarily.
No.
Because
I'm giving you the definition. That's what I mean by Boolean algebra, the one that we are looking at.
No, usually I think there's a different definition. Doesn't matter. It's like as soon as there's only one binary operator required to actually.
I understand. I understand. I know. That's not what I'm saying. What I'm saying is when we're looking at these 16 ones, right? Is the combinator one interesting, favorable because we are doing term rewriting of only two kinds of terms of characters instead of 16? That's the question.
No, I don't think it's completely unrelated that there are two characters in the combinator case. I mean, two characters like S and K.
Yes.
I think it's unrelated. That's like two Boolean. We can model anything with those two S combinators.
Yes. So okay. So that's another point of interest. I'm just trying to extract the interesting combinators, or justify and make explicit also for viewers that the interest for combinators is that yes. So on the one hand, it's just two of them instead of 16 in the list of Boolean algebra.
Yes.
Also that they are universal because they can implement anything you want. This kind of thing. I mean, this is the kind of thing I'm trying. I'm unfamiliar with this stuff. I mean, I'm asking because I want to learn as well.
Oh yeah, sure. Yeah. To put it in slightly different terms, right? I think one point I was making either during this live stream or earlier is that instead of having to take, and, or, implies, etc., we can do it all in terms of just S's and K's acting on these truth values. If that's the point, then yes. I mean, I think the fact that you can do it just with S's and K's, or again, it can be anything. I mean, there's nothing special about S and K as letters. But the fact that you can just do it with S's and K's, on the one hand, signals to me that it's more parsimonious and that it involves less than if you had to have these 16, or guess.
Yes, but then
particular
Nick's
operators.
point. But then James, Nick's point is what I was going to mention as well. That in basic Boolean algebra, you actually only need 3. You only need or, and not to implement all 16.
You just need one. You just need
You need
NAND or
NAND.
NOR. NAND or NOR is sufficient to
Just NAND. Yeah.
yeah, that's the whole deal with the Wolfram axiom, at least.
Yes.
It's the shortest one. It requires the single axiom, by the way. It's not the shortest, but also shortest in the number of the axioms you need. You only need one operator and one axiom in order to formalize the Boolean algebra.
Sorry, I missed that. So one operator. Which operator?
NAND.
NAND.
Yeah.
So it's either this one or is NOR, or this one.
So compositions
This is it.
of NAND give you that.
Yeah, this is universal. So by just composing NAND or NOR together, you can get all of the other 16 ones.
Okay, yeah, sure. Of course, I mean, we know that because of this, we know that it's going to be only 2. But what I'm saying is that the traditional presentation of Boolean algebra is not widely bigger than that. It's just 3, right? So I'm kind of asking for, I mean, I guess one of the points of combinators is that they are universal in the sense you said. But if I look at traditional Boolean algebra and I have and or not or NAND and NOR or whatever, I mean, these are formally equivalent, right? In the sense that they are a rewrite system with this few operators and they have truth tables and they work, right?
You would also, I mean, technically, you'd also need like equals or implies as well, right? In order to really do.
Oh, it's going to be
Boolean algebra.
different implies, different equals. This is one of them is a logical connective. If you actually formalize equals like from this table using NAND or NOR, it's one equals, and another equal is just when you want to do some theorem proving. You have to separate those.
My entire point, I don't want to muddle the waters because my entire point is economy of number of operators is a point, right? It's relevant, right?
Yes.
Okay. That was my entire thing. Yeah. Okay.
You're making a good point though, which is, especially if we just did it in terms of NAND. Yeah, I have to think about this actually. I mean, because someone could come and make the argument, you can do all Boolean algebra, like the Wolfram axiom is an example of this. Like you don't need to use this whole kind of assortment of different functions. And then the question is, so what's so special about the combinator case? You're saying that there's some, it's more foundational or it's more parsimonious, but what exactly does that mean?
Mm-hmm.
Right.
Yeah.
That's something to think about.
Yeah, that's very interesting. I mean, I'm very satisfied with this. I learned a lot.
Well, good. Well, I thought this was a fun first meeting. We actually, I mean, for viewers, we've had a lot of, or not a lot of, but we've had a number of kind of logistical meetings, like who's going to bed at what time, and how is the institute, running, and who's responsible for what. So this is, I mean, the whole point of this ultimately, notwithstanding everything else that's happening at the institute, it's exciting, like events or partnerships or what have you. I mean, the key thing is the research. And this was kind of fun. I get some sort of sense, not to speak too prematurely, that like I get some sense for our different intuitions, and each of us seems a little different, maybe even quite different.
That's good.
Which applied to this project is quite, and applied to projects generally is quite good. I hope that the audience, the viewers, I don't know how many viewers we have on day one, but for everyone who's watching this, thanks. Feel free to if you have any questions or if there's anything that you're interested in, you can of course join our Discord. You can access our Discord through wolframinstitute.org, as well as our Twitch and our other social media platforms. Feel free if you have questions, comments, you want to work with us, you want to support with us, you want to support us, you want to work, anything, feel free to contact us there. Carlos will be there, Nick will be there, I'll be there, and we're happy to chat with people all the time. We will have a live stream tomorrow. It'll be about a completely different topic. It will be in metamathematics, so anyway, we'll see you there. But yeah, we look forward to doing this science in front of you, and this was the first one. So yeah, thanks everyone, and see you soon.
See you soon. Thank you, everyone.
Unless anyone else, unless there's something, I don't need to have the last word. Is there anything else that needed to be said?
I mean, I think there's a very productive first stream. Sorry, go ahead.
Just it's a logistic. Should we upload this notebook into some archives for everybody?
Yes. So the archive is getting set up on the Institute website. So I should say, yeah, I should make a comment. Actually, I'll make a comment on the Discord page as well, that part of our open science practice, in addition to live streaming, is the archiving of all of our notebooks. That archive is just not yet available on the website because we have a kind of the initial puppy version of the website that was made available for the launch, but that puppy is going to grow and grow and grow. So that is one feature that will be introduced soon. It's just not ready quite yet.
Yeah.
So basically, Nick, what we're going to do is we can store them. We have the storage for the email suite. We can put them there. And once everything's ready, there are two things. I mean, now this is somewhat insider stuff, but I want to get it configured so that we can do something similar to what we did with the physics project website, where we can basically upload these documents to whatever file system we have. Yes, and then it automatically uploads to the website so that we're not doing it manually.
Oh, just one line of code. We have to set up a nice cloud ID associated with the institute, like that. Right? Just upload. There's a link everybody can use, but it uploads to the one associated with the institute, and not whatever I have connected with right now.
I should put you in touch with the people who are working on the website then. Yeah.
All right. So let's say goodbye to the viewers and then we can have a quick logistical note after this. All right. Goodbye, everybody.
Logistics always creeps in. All right. Thanks, everyone. Cheers. Take care.
Bye bye.